My name is Derek Ellsworth. This is Penliang Yu. Both of our names are on the syllabus. This is the last time we'll meet. So today, except for perhaps the presentations, so this is kind of an organizational meeting to kind of set the stage for the way that we run this web-based class. So this doesn't have to be a meeting time that you keep open, and of course that's good for the people who haven't joined us yet, because obviously it's not open for them. What I want to talk about today are really the syllabus, how things are on Canvas, and also the other resources for the class. So perhaps the easiest place to start is on Canvas. I just logged into our course webpage. And so many of the things that you need you'll find on Canvas. I guess the most pertinent ones are under this syllabus tab. I guess I should switch it to student view, so you won't quite see this. You'll see this. The other stuff is my personal page. And so I guess the class is on numerical modeling. I think it's one of the 4 or 5 classes in the EME graduate program, which is a required, one of the concentration classes. Maybe you need 2 of them. I forget exactly. The rules seem to change every year, so I'm not quite sure. But this serves as one of those core classes, I guess it is. And it's a class on numerical modeling. And so for this, we have a course resources page, which you probably don't need to know much about. But it serves to you, that's curious. It serves to you some things, which we'll talk about in due course. And it has the individual lectures thing, but you don't have to access them through there. These are just the screen captures that I captured in 2015. These are 2016, I think. It's the last time I physically taught it in person. And so those are the medium by which are used in this. The syllabus, which is on that main page, is also here, which is what you have in your hand, which we'll talk about in due course. And we'll also use this timetable for the class. Penn State classes are 15 weeks, 8 weeks before spring break, 7 after. There's a lot of latitude, of course, when you do these, when you do the class and when you do the follow-up assignments that are related to this class. And so I think it's quite useful. So if you think of yourselves as consumers, which of course you are, then this should be something that I hope you like. I hope you don't get put to sleep by the lectures. There's some tendency sometimes to do that, right, when you're looking at things online. So I thought that we might look at some of these individual components. So perhaps the first thing to talk about would be the syllabus. We'll do that, easy enough. And so you can see the actors, myself and Penliang. You don't need to see us again after this, but if you need to find us, I guess it's a web class, so I shouldn't tell you where we are. But my office is in 231, just around the corner, and Penliang's is right next door, 238. So if you need to find us, you know exactly where we are. And what this class is a class on numerical modeling of physical systems. Mechanical systems, fluid flow systems, fluid transport systems, heat flow systems. And the medium by which we use to teach it, it's all in what I would call finite domain models. So things like finite differences and finite element models and volume-centric models. We use finite element models, so all the models used in this class look at using a numerical technique called finite element models. It was developed, as you'll see in the first introductory lecture, which is not today, in the 1950s by 2 guys. One guy called Ray Clough in Berkeley, who was working with Boeing, developing flight structures, part of the Cold War. That's what was going on then. And a guy called Agiris, who was working either in Aachen or Imperial College in London, who came up with the idea at the same time of how to make a much more flexible method of solving partial differential equations than finite difference methods, which up till that time had really been done just on a rectangular grid. So this allows elements that can actually take the form of the structures that you are representing, and therefore is a little more versatile. It's a bit like finite difference methods in that all the calculations that we do can be localized around a single node or a single element, and we can talk about the characteristics of those elements. And the deliverables for 50% of the class are that you code to some subroutines which define those individual elements to solve a problem. It's really quite much more straightforward than perhaps you might think from what I'm saying now. And we'll talk about that in due course. And so the class in general starts off by talking about mass and energy transfer in the first part, which is this, after introduction. And the first topic is to look at fluid flow and diffusion. So diffusion means pressure diffusion of a pressure pulse in a porous medium. And it's the same standard way of looking at the system for each topic. We talk about one-dimensional problems, one-dimensional elements, which look at linear fluid flow, steady state. And then we branch out to talk about two-dimensional problems. And we talk about multi-dimensional problems. And first of all with triangular elements, which are the simplest, and then with slightly more complex ways of doing things, with rectangular elements, and elements that have lots of extra nodes added to them to allow us to more accurately solve the equations, and then talk about how we generalize it in 3D. And it really just follows from this first idea that all the concepts follow basic behavior in 1D and to extend it to multi-dimensional problems. And then once we're solving problems that look like this. Don't know if you've seen this terminology before. These are second order partial differential equations. So you'd see something that looks like permeability d2p dx squared equals compressibility times dp dt. And so the first part is dealing with this left-hand part, equals 0, where this equals 0, and the final part is looking at transient behavior. And so that's the format that we attempt to repeat for each of the physical problems we're trying to solve. So the first one is to deal with pressure, fluid mass flow, the mass flow of water or gas. The second one is for advective transport, when some quantity, it could be contaminant or minerals dissolved in water, which are carried by the bulk motion of the water at some velocity. And the term representing that is this advective term here. Or it could be heat flow, where in addition to conduction, which is really just represented by this equation here, this is a conduction equation, same as steady state fluid pressure flow. When we look at conduction in the system, that is represented by this term here. This is the transient part. You'll recognize they marry up exactly with these parts. And the extra term is to take care of the property, either heat or mass. Heat carried within a fluid, or mass carried within a fluid, that is advected in the system by the motion of that fluid and therefore travels with it. And so certainly in the Earth's crust, certainly in geothermal reservoirs, certainly in contaminated reservoir aquifers, the mechanisms of diffusion, i.e. conduction, and advection both go on hand in hand. One might be completely dominant, in which case you can get rid of one of the terms, but they might both act in unison and to similar magnitudes. So in many cases you can ignore one of them, but in some cases you have to accommodate both of them. Again, you'll see the same format is 1D flows, multidimensional behavior, and then time-dependent response. And I guess for transport we also talk about the fact that some of these species that are carried from upstream to downstream may also react with each other and transform as they move along that flow line. And it's a relatively straightforward way to be able to accommodate that. So none of this is super difficult. If you have a decent science and or engineering background, all of these things will be readily accessible to you, I think. We talk about fluid flow in terms of fluid mechanics. And so these flows that we've talked about here are just what might be called creeping flows. They're occurring with no inertia involved. Accelerating the fluid is not included. And so we don't have to worry about Newton's second law, F equals ma. So a fluid, when it goes from upstream to downstream, if it accelerates along that flow path, we have to accommodate for that acceleration. And so very briefly, we'll talk about a set of equations which are referred to as Navier-Stokes equations, which are a bit more complicated, that require a momentum balance equation, which is basically F equals ma, as it turns out, where sum of forces are equal to the sum of accelerations, and a continuity equation, which is mass in equals mass out. That's all it is. No accumulation of mass in this second equation here. And we'll spend a very small amount of time dealing with that because that's not really a focus of the class. And then we'll talk about momentum transfer in solid mechanics. So solid mechanics, when you deform solid bodies, when you crack solids or compress solids, you stand on the soil and you compress it, is what we'll deal with. And again, we'll talk about one-dimensional elements, multi-dimensional elements, and we'll talk about time-dependent behavior. And so when we look at this, one way to think about this is people talk about coupled process modeling. Or coupled processes modeling. And sometimes they use an acronym for it, which is THMC, where each of these refer to chemical reaction. Mechanical compression. I guess deformation would be a more useful term. Hydraulic flow. So my writing may be poor, but hopefully you can read it. And thermal transport. So my reason to mention that is that if we look at each of these individual components, then this is hydraulic flow and potentially heat transport. This is potentially heat transport only by diffusion, conduction. This would require that we know the underlying flow on which the advection relies, and in addition we might be interested in the advection of temperature or the advection of chemical components. And then when we get down to the bottom, we're dealing with mechanical behavior of solids. And so the point is that individually we can look at these separately. It turns out that the expressions that we deal with for each of these are actually have a common framework to them because they're similar physical processes. Fluid flow and diffusion follows Darcy's law, something like V equals permeability divided by viscosity, pressure gradient in space. Temperature follows Fourier's law, which is heat flux is equal to thermal conductivity change in temperature with space. Chemical transport is Fick's law. Don't remember whether it's 2 R's or not. Darcy's law. So depending on your background, you might have heard of these laws. This would be Fick's second law. For chemistry, and that is that this is a thermal flux. Fick's law is that a mass flux is equal to, should make sure we have the minus sign in here, is equal to the diffusion coefficient for that flow times the gradient of concentration. And you'll notice, of course, that these laws link a gradient of some quantity in space to a flux, a velocity or a heat flux or a mass flux. And of course, even for mechanical behavior, this would be, going back to this would be Hooke's law. Which links momentum flux of sigma equals dE. So du dx times modulus is equal to stress. And actually you could think of this as a momentum flux. So this is Hooke's law, and of course the components of this are that this is a displacement gradient. Some people would call it strain, how displacement varies in space, and this is a momentum flux, which we just defined. So the point is that all of these expressions that we've talked about, Darcy's law, Fourier's law, Fick's law, and Hooke's law, go into some kind of framework of partial differential equations to conserve something, to conserve thermal energy, to conserve mass, to conserve momentum, or to conserve mass as in dissolved, or heat, I guess. Heat is the one I didn't mention. And so it's not surprising that the equations that come out of these start looking the same. So the first part of the class is to understand those individual systems. It's really, once you've covered the first system, the other stuff should actually start getting a bit repetitive, and you might hate it, but nonetheless it follows in some reasonable way. And so the other objective of this course is to then allow you to understand how you can solve problems where, for instance, these processes all interact with each other. So one example of an interacting process for this might be a nuclear waste repository. So you take reactor fuel, you vitrify it, you build a repository underground, you put it underground. It's still got radiating heat because it's got a half-life for some of the elements for 100,000 years. So it generates heat, it heats up the rock around you. That heat changes the stress field. That stress field opens or closes fractures around the repository. That changes the transmissive characteristics of those fractures for their fluid transmission characteristics. You break open the flasks inside the repository, the stuff leaks out. The mechanism by which it gets to us on the outside is by being carried by water flow. If there's water flow, that's a problem. So you want to keep it very low permeability. So you can look at the interaction of the heat, changing the temperature regime around the repository, influencing the thermal stresses, probably building them, maybe fracturing the rock, maybe creating fractures, and then that allows flow to occur, which has to be all coupled together depending on how closely interactive all those processes are. Some of them might be so loosely interconnected that you could calculate what the thermal regime is, and then calculate the stress regime, and then just use that information to calculate what the flow regime is with the modified distribution spatial distribution of permeability is. But some of them might be coupled because the water coming out of the repository, gets affected by groundwater, which is let in. The groundwater is cold, it chills the rocks. There's some feedback on reducing the stresses, therefore the permeability goes up, and you have to deal with it in a much more coupled way. And so our entree into this is to be able to do that. So the theme of this is to be able to look at doing what we talked about there. Let me see. And then at the end of this, I guess we talk about coupled processes. So we'll talk about how to combine all these equations together in a simple way, by a variety of different ways. And we won't talk about XFEM. You might choose to do a project on that. And then to finish off the class, we'll talk about alternative methods. So all the methods up to this point here, would be finite element methods. And though we'll talk about, so these are domain methods, as you'll find out if you don't already know, which means you have a physical problem, you cover it with a mesh, a lattice, and you calculate the behavior at each of those mesh points or node points, and so you have a very big set of equations to solve. Integral methods mean that you just define the boundaries of your problem, you mesh only on the boundaries, and you use that to solve throughout the interior of your problem as well. And they're just a different method. And you'll find out about those. I won't explain what they are. I can't remember whether to talk about smooth particle hydrodynamics. Some might choose to do presentations of that. Might talk about discontinuum methods, DEM methods, and I don't think we talk about this, so that's not in there. So in terms of grading, the class is a cinch. It really works, I guess, on my worldview of life as a graduate student and as a past graduate student. You'll do what you want to do. You'll get out of a course what you want to get out of it. You can lead a horse to water, but you can't make them drink, so I don't need to do that. So all of these assignments, which we'll talk about now, you do. They're quite straightforward, and they allow us to look at each of these transport modes and mechanical modes and coupled modes, both for steady state and transient in each of them, and to develop these subroutines to solve the problems. And then once you've done it, you have to tick a box to say that you did it, and that's it. And so that's the deliverables for 50% of the course. So you get 50% of the course, hopefully, for doing this, because I think it's a learning experience for you, but you get that nonetheless. And the other half of the class is to do a presentation on a topic of your choice. And in the past, we've allowed people to at least choose a ranked set of topics and then try and marry up the most desired topic with the individual. And so there'd be presentations typically in groups of 3 for an hour and 15 minutes, the length of what this class would be if it was on a Tuesday, Thursday. And through COVID, we've certainly migrated to creating them on PowerPoint, the students narrating them, and then converting them to YouTube, to MP4, putting them up on YouTube or somewhere else, and then the other students reviewing them individually with a series of 10 questions that the group would present for their presentation. So it's pretty straightforward. So the different topical areas are these. There's a little wiki attached to them in each case. There is also one for peridynamics, so it's not on your page, but it's on the website page. So SPH is smooth particle hydrodynamics. It was developed for exploding stars, and basically what it does is it takes a star as a mass, and it uses Newton's second law, F equals ma, to solve its migration through the system, and solves it incrementally, as if it was, you could think about it being used for crashing waves. It's found lots of application in free surface wave behavior. The wave, you represent each little volume of the water in a wave by a block, by a sphere that has some mass, and you allow it to evolve according to the forcing that's given to the wave, and you get a solution for it. You get very nice solutions for it. Lattice Boltzmann methods are dividing a lattice into a very fine lattice and then solving between individual nodes. Typically it's used in looking at porous flow, say in CAT scan experiments. You divide the porous medium that you see in the CAT scan into voxels, and then you divide them finally to look at Navier-Stokes flow within those capillary tubes and porosity, and be able to solve for flow within the sample, for instance. Phase field methods are usually finite element methods that were developed for looking at the solidification and melting of alloys, places where you have complex boundaries, but they use generally finite element methods to solve them. Extended finite element methods are finite element methods which are typically used to solve fracturing problems. They've been used in lots of problems where you generate a fracture and the fracture propagates through your porous medium, through your medium. If you use conventional finite element methods, then what you have to do is you have to remesh as your crack grows to be able to accommodate the fact that the crack is growing. Extended finite element methods allow you to keep the same mesh but to follow the crack as it goes through other elements and deal with it in a very specific, not so complex way, but quite an elegant way. Boundary element methods, well, we set up here, we talk about infinite domain methods or integral methods. So these are methods where you apply nodes and elements only on the surface of the problem you're solving. So if this was the deformation problem you're solving, instead of making a lattice over the face of it, you just mesh elements on the edges and then solve for the behavior within it. And so it's quite an effective problem. It's quite often used actually in things like hydraulic fracture propagation, dike propagation, because you only have discretized the edges of the propagating fracture, not the whole volume that sits around it. Discrete element methods basically take a granular mechanics model where you take a pile of sand grains, you represent each sand grain as a ball, and it has mass and it has velocity, and you solve Newton's second law by double integrating the acceleration term to be able to solve for the motion of all these interacting balls as they collide and bounce off each other. And it's used broadly to solve problems like that and much more sophisticated problems. I'm not sure what I mean by lattice problems in that, so I don't know. And peridynamics is to take care of very nonlinear problems using finite element methods. That's probably, I won't say much about that. References, I don't think you need them, but they're there if you need them. I don't think we need to say anything else about the things on there. So, questions before I go on. Some people might be joining us. I know it's kind of drinking out of a fire hose, perhaps, I'm not sure, but I think we're really just talking about the dynamics. You don't need to understand anything about the mechanics of what we're going to do inside each of these. I guess today I'd just like to explain exactly what we're going to do in terms of the mechanics, if you like, of the course. So you now know what the general course is, what it covers, what the topics are. You know what the deliverables are in terms of 50-50 for these subroutines to program and the presentation. So let's talk a little bit about where those things are served to you. Syllabus is online. We've just gone through that. The course notes for this, well, they're not great course notes. They're a bit rough and ready, but I think they're at least utilitarian. And they're what are used in the recorded lectures. In the same way that I'm doing this to write up things, sometimes write on the board, the whiteboard on this. But those are available to you. I don't think you need to study them in detail, but maybe you want to go back to them after you've looked at the material. I don't think you need to go to YouTube, but all the things are present on a YouTube page for the class. These same videos that are here are all posted on YouTube.
So we talked last time
about see what
about
kind of things are going on. Did it open up another page? Yeah. We use a bit of a cryptic, but a very simple finite element code in this class, which I wrote, which is cryptic because it's not really heavily documented, but it's pretty bare bones. it does actually all the things that we need to do in each of these THMC modules, and it is also able to link those if you use it carefully, cleverly, perhaps not carefully. And so I'm asking you to develop subroutines that allow you to run that. So there's an incomplete version of the code which has these subroutines which are not completed, but they have the bare bones in them and some pieces missing, directing you to add the missing pieces. And the idea of this is that all finite element models work on the idea that you're solving a big mesh, but it's divided into individual elements. You can take a single element out of that mesh, and you can solve the equations for deformation or flow in that single element, and then put it back into the system and go to the next element. So it's decentralized. You can break it down into the behavior of a single element, so everything decentralizes into the response of a single element. So what's usually done is you make a mesh, you define some conditions, material conditions in that mesh, permeability, modulus, thermal conductivity, etc. The computer assembles that mesh, and then it goes individually to each element that you see. It pulls it out. It has the nodes of this element, so it knows its size, it knows the materials, and it develops what's referred to a stiffness or a conductance matrix, which it then sends back and puts it in a very big system of equations which represent the whole system. One element is one portion of that, and the rest of the equations all fill that out. It applies boundary conditions to it, and then it solves that whole system of equations, and then it comes back, and then it uses that system of equations again to sort out what the interior behavior is. So the point is that everything is done in a localized fashion, not solving the whole system of equations, but just defining these individual behaviors. So the incomplete model has those element subroutines, as we'll call them. We'll look at them in a second. And they're not complete. I'm such a good guy that there's actually the solutions there available. Perhaps you want to try not using them. But again, as I say, my point is that you get out of a course what you wish to get out of it. You've seen this already, I think, on one of the things we looked at. This is kind of a schedule for the different assignments and which subroutines, they're all MATLAB codes, and which input files you use, and what they do. We'll talk about that perhaps a bit later. And ultimately you'll make a presentation on one of these topics, so we can talk about that. So that's kind of it. I guess in terms of presentation tasks, it's not very onerous, this class. I guess this might be presentation tasks. Yeah, okay. So we switched to doing this online in the spring of 2020 for obvious reasons. COVID came along and we were off campus. And so we'd normally done this with interaction, so everyone was sitting in their basements or their parents' basements or doing something. I don't know what they're doing. And so there wasn't, come in, do you want to grab one of those things there as well as you come in? So there wasn't any interaction necessarily going on except through social media. So I put this together to try and get people to define what their responsibilities are in making the presentation. And so some document like this should come from each of the groups, which we'll put together after a couple of weeks. And it's really just to define what the project is that you've chosen and that has been ratified that you can work on. To identify maybe a leader, doesn't really matter. Identify whether you want to do it in person or online. They were all online that time. And then to define who deals with each of the parts of the presentation. So you'll see as you go through the class that all of my classes, I want you to make a presentation in my image, I suppose, in some respects. So this is the kind of format I use for each of the topics. I have an introduction to say what we're trying to do. I talk about the historical perspective, that the development of FEM was by Ray Clough at Berkeley and Agiris in Aachen and Imperial College, and it came for this need in the 1950s that all of a sudden space flight structures were intriguing and important, and all of a sudden the digital computer was here, and of course space flight structures, wings, don't really lend themselves to being finite difference rectilinear grids. They're much better for finite element models. Talk about the general principles by which it works. FEM works on F equals ma. What the equations are that describe the system and how those are developed. Try solving a hand calculation example. Very easy for finite elements, because finite element method, you can pull a single one-dimensional element which has two nodes on it, and you can absolutely work the equations out for that, which are 2 by 2 matrices without any problems. You can even do it for triangular elements, which would be 3 by 3 matrices or 6 by 6 matrices, and show how to do it by hand. And the reason for this is that I don't mean this to be a presentation to a professional meeting where you're showing off your research, but more to your colleagues and peers who might be seeing this for the first time and would like to learn how to do this, and in an hour and 15 minutes might get a pretty good introduction to be able to replicate the things that you've done. That's the goal. To solve an example numerically, maybe following on from that hand calculation, or to code it, some people do it, and then to talk about how this particular method, SPH, lattice-Boltzmann, has been used by others to solve different problems. And so we're not casting you adrift in this. Again, I say this is a pretty straightforward class, because I think there's lots of resources available to you. Because if you look at the bottom of this course resources page, well, this class has been going on for longer than I can remember. You can see the dates on it, and it predates that as well. And these are the examples from previous presentations. So I make no warranties.
Hello, everyone.
For
We are the
how great or not great these might be.
element method group, and the group is composed by
29 minutes. Is that
Emily
an hour and
Saucier,
15 minutes?
Gabriel
I'm not
Santos,
so good at
and
math,
Young
but
Chol
I don't
Kim.
think that is. And so you'll see these things. Actually, I think this one, actually, I thought, even though it's 30 minutes, I thought it was a
The
really
theory behind the
a
boundary
very,
element
a very
method.
cool.
I'm going.
They did some nice explanations for the solution, the governing equations, and how to move it. The problem with boundary element methods is that, unlike finite element methods, where you can take a single element and you can do all your calculations in isolation on that element, boundary element methods, because the elements are meshed around it, this element here influences this element here, and so you can't separate them. The essence of the method is the interaction between the elements, and so you can't just pluck out this element and deal with it. And so that's quite a difficult thing, I think, to wrap your head around and to be able to explain to people. But I thought these guys and gals, I heard a lady's voice there, did a nice job on that. And so how am I going to get back? I guess I'm going back through here. So there's lots of examples about all of these. Apparent that's the first time we did FEM-DEM, coupled finite element and discrete element methods. We did that because I think 6 people wanted to do discrete element methods. So instead of doing a group of 6, which is kind of cumbersome, I split them up into 2. And this is actually an interesting way to modify it. And so that's it. So you can see those. So I think by the end of next Thursday or by the end of next weekend, I ask you to rank your choices for those multiple topical areas. And then I'll go through them, and Pen Liang and I will go through them and try and hopefully give you the one you want and try and figure it out from that. We leave it for a couple of weeks because people may transfer in here or drop out of this. You may think that after today you never want to come back here again. So that's why we leave it for a week or so to do that. And that's it. So that's kind of what's going on. I will say that you can download the finite element program. What else do I want to talk about? You probably, all of you would be at least second semester people on campus, so you've used Canvas before. Everyone's used Canvas before, certainly. It's not so, I don't need to belabor that. I will ask if you have questions. I still have some stuff to do, but any questions so far? Oscar?
There are YouTube videos and lecture videos. Which one should be watched?
Okay, that's what. Yeah. Okay. The lectures are best accessed through Canvas, and so next week doesn't like me because thinks I'm a student trying to steal all the answers. So next week, the assignments, everything is posted to do on Canvas. The assignments are, this will be due by January the 21st. You can work out when that is. It's to give you a topic. Just reply online on Canvas with the rank topic. Group presentations won't come alive. So this is, that's not that. These are the assignments. No, okay. Group presentations. Oh, these are me. Okay. Where have my assignments gone? I looked at them today, I thought. No. That's a bit of a problem. What am I not doing? No, these are the presentations. So am I, what, did I accidentally delete them or something, or am I not going far enough down? 50%. Am I still in student view? No? No. I don't know. What? Oh yeah, perhaps that's what it's referred to as. Oh, see, it's not very difficult to do it, but of course you'd like to find the material to do. The material served to you on Canvas, so I'm not sure why it isn't there right now. So each week I will send you an announcement. You'll get an announcement coming out at midnight tonight. If I get out of student view, because it's not there. Tonight there will be an announcement, and it will be week 2 deliverables. Oh, there it is. Okay. That's why I don't see it, because it's under announcements. Silly me. So each, if you have insomnia, on Friday morning, at midnight on Thursday, you'll see this come out. It'll be served to you at midnight on Friday morning, on 12:01 Friday morning.
So this is EG.
You get the picture, so you start seeing similar things. I think this might be explaining the course conduct. Probably can go through quickly for that. Looks very similar. Guess I could cut the sound. And so there are 2 videos. This would be for the Tuesday class. This would be for the Thursday class. So for each week there are 2. And then according to these, once you get through them, so the next one would be week 3, which of course would come out the following week, and it would look the same again. And also, as a student, you'd see, if you look at the syllabus, the deliverables would be these individual parts here. So the deliverable is what we just looked at, and it would be to develop and implement a subroutine to do some certain thing. And then if you want to take that quiz, the quiz is easy. Yeah? I can do that one. So let's talk about what that assignment entails. So what I was going to do was I've downloaded the finite element code. So maybe I'll get out of this. So it's here, it downloaded onto my downloads, but I just had a previous version on my desktop. It's a zip file. Should be able to open it up. I'm not going to use that. because I think the one that I already have is a duplicate of it. So how can you see that well? Is it big enough? So all the material is in .m files. It's in MATLAB. Does this get bigger if I do this? It does a little bit, but it's not very clear, is it? Oh, it's not bad. And so these will all run in MATLAB, and so you can choose to use MATLAB if you wish. You could also use something like Octave, which is free and runs on both, which is MATLAB GUI, GNU license type thing. I tend to use a program called FreeMat, which is also a Mac version of a MATLAB lookalike, free version of MATLAB. And I don't know if I'm already in there. If I use my documents on you, looking for the desktop. So if I find desktop, if I open these files, so I'm going to do a quick example, which I should have desktop in my sidebar. There's probably a faster way to do this, but just bear with me. So these are element subroutines, and I'll explain to you what those element subroutines are. So these are the things that you need to modify. And this is the last one. Input. So, we go back to what I had in Notability. You've already seen this this form here. So this is, from what we've talked about so far, you'll recognize, I hope, some of these things. These are the weeks, 15 weeks for the class. We don't use it to the bitter end, but we do it for the first 12. These are the topics, so this would be flow. You chose a bad place to sit, Penny Yang. I see you trying to look through me. This is flow, so this would be H. This would be transport part, which would be C. This would be solid mechanics, which would be M. So this would be H, C, or T, I suppose. And this would be M in terms of hydraulic, chemical, transport, or thermal and mechanical. And these are each of the classes related to this. And so this is the Tuesday class, this is the Thursday class, these are what they talk about, so they're all laid out in that regard. And these are the individual assignments as deliverables. You should move along the bench. You can see okay? And so the notation for this is described in the bottom. So the idea here is that for flow, the second number represents, 1 is for flow, the second number for transport by convection is 2, for solid mechanics, the moniker is 4. So you see that for each of these, and that changes for each of these here. So this would be Navier-Stokes flow. It's kind of a small part. And the second part in this refers to 1D or 2D, right, as the tops say. And so we start you off running. We start you off walking before you need to run. So we do a simple 1D problem, and then 2D problem, probably a transient problem in there somewhere, as you'll see down here. And so this is the kind of makeup of the individual elements that you need to develop. So in terms of the weeks, this is where we are today, Thursday. I guess we're here. So this is where we continue. Next week, no assignment. I guess at the end of the following week, week 3, then there's assignment to do a one-dimensional problem for flow using this input file. And so the input files are named in the same way. I guess that's not right. This is the input file we use today. So element 1, one-dimensional element for flow is this 1, 1. Problem number 1. One-dimensional element for flow, problem number 2, problem number 3, etc. Just there for your convenience. You can use them as you wish. And if you go back to this, then at least if you're unsure of yourself and don't know how this stuff works, then FemRun is the overall controlling routine that runs the system. What it does is it looks for a particular element subroutine, in this case the one-dimensional flow routine, which is 1, 1, 1. And that element subroutine looks for input according to that element as well, 1, 1. And so they're all arranged. And so the finite element code for this 1, 2, or 3-dimensional static and dynamic and also coupled process routine is only something like 150 lines of code. So it migrates, it gets all the data in, it puts it in the right places, it goes to the element subroutine, you've done something to that subroutine to change it to do exactly what you want, it brings that stuff back into a matrix equation, it solves that matrix equation, and then it uses the element subroutines again to interpret the results you have to give you fluid pressures and fluid velocities everywhere across your mesh, whatever that is. And so that's the whole essence of finite element work. And so to run this, you'll be able to see this in a recording and also in the stuff that you look at. I think this runs now because it's to run, oh, actually, I won't look at it now. So you see that it's taking the input data, which is from this file that we're defining, which is up here. Just making sure it's still on screen. So it uses this. It absorbs the data in a standard way. It zeroes out some matrices, and then it does this localizing. It goes to the data and defines what the material properties are for in the particular element. It sends those variables to the element subroutine to make the matrix equations that form that element and then come back to the main program. It puts together a global system of equations, number 3. It puts some boundary conditions on them, item number 4. It rearranges those. It does that all for you if you put in the right data in number 5. It solves the systems of equations, and then number 7, it spits out the results. So that's what it does. And it's 150 lines of code, very compact, you can understand. So it's not the equation, it's not the COMSOL or the abacus that you'll use on the cluster at Penn State, but it does force you to think about the data structures and the methods and the way you might formulate a problem to solve it and how those programs work, because those programs work in exactly the same way as this. It uses something called dynamic storage allocation, and they use the subroutines the same way, developing the matrix equations and bringing it back to a main uber large matrix equation, which it then solves. And so I'm not sure that we need to understand more about that now, but I will run it. So it's loaded. If I run it, it should run, and it runs in the background here. I guess I won't make it full screen because I might want to make the screen larger. So the screen's a bit larger there, so yeah, you can see it, but it's too close. So this is the solution, and it might mean nothing to you right now, and I'm not sure it's very useful for me to go through the expressions, but what I could do, I suppose, the one thing I didn't look at, guide you through, was on the course resources page. easiest way to find it, that's a big face, is to look on the the home page for this class, which is here. This is the course resort, or you can navigate from Canvas. I didn't download the course notes. I don't need to, I guess. But if you look at, they're very messy. They're typical Ellsworth notes. But I'm trying to find, and too much. You don't need to read all this. You need to see the stuff that we use in class. So this is fluid flow. And the geometry here is a dam. And the idea is, I guess I can't write on it because it's on a PDF, but the idea is that water flows from upstream to downstream. And maybe you could represent this dam with a permeable layer that flows between these two parts just by two elements, two one-dimensional elements. One node here, and one node here on this element, and one node here, and one node here on this element. We give it two different material properties. Its hydraulic conductivity is twice as high in this element as it is in this, and therefore the head loss across this system should be twice as big here as it is on here. You don't need to know that now, but that's the case. And we can use the idea of a localized element. We describe what an element looks like, and this is what the element subroutine is based on, this particular geometry, where it goes out to the element subroutine and then brings some information back. So this is the geometry that is put together. So what we prescribe is that the upstream head here is equal to 25 meters. The downstream head is 20 meters. And we don't know what this intermediate value of head is. And we know that the head is defined upstream and the head is defined downstream. So the unknown is the intermediate head in the center. But the other unknown is the complementary fluid velocity, the flux that comes in through the upstream boundary and goes out through the lower boundary. So we want to solve, we prescribe the upstream head, the downstream head, and the fact that the flux at this intermediate node is 0, because the same amount of fluid goes out of this element that comes into the other element. They exactly balance each other. And the unknowns that we want to determine are the flow volume rate here, the flow volume rate here. They have to be the same because it's a steady problem. And the unknown value of the head, which is going to be intermediate to these. But as I just said, it's probably going to be closer to 25, 2/3 of this amount, because the conductivity here is half of this, and therefore the head loss in here is twice as much as it is on the upstream part. And so, regardless of all the other parts in this solution, and you can use this to benchmark it, to give you some bearings, is that these values that we have here relate to that. This is the upstream head at node number 3. This is the downstream head at node number 1, perhaps, I guess. Yeah, it is 1, 2, 3. And this is the intermediate one. It's 23.33, which means that it's 2/3 of that magnitude drop. It's not intermediate. It's not 22.5 because of the difference in permeabilities or conductivities of those media. And its flux is equal to 3.3 times 10 to the minus 6 out of the system, negative, and 3.33 10 to the minus 6 into the system. They exactly balance each other, and because it's a steady state problem. And the flux at the intermediate node halfway along the system is 0 because the amount coming out of one element, the upstream element, into the downstream element exactly balance each other. So it's 0. And so that's kind of the background of this class. It's set up not as a learn how to use COMSOL software. It's really set up to learn how the techniques work, and the techniques that we use, albeit in this kind of microcosm, are applicable to other coding things you might do for yourself to develop finite difference models in terms of the data structures and the interactions between all of these things. And of course, if you can understand how this works on this stage, it gives you insight into when you make your COMSOL or Abacus model and you spend 2 days figuring out why it won't work, and then all of a sudden you realize it's because you're meshing elements and you go from elements which are 1 millimeter to 2 kilometers in the same system, and numerical problems don't allow it to work in those circumstances. So that's kind of where we are with this. So that's all really I have to say. Penny, do you have anything to add? No? No? Any questions? Very quiet. I presume it was all so clear that that's why you didn't ask any questions. So, it's, yeah. Yeah.
I need some clarification.
Yeah.
Because modality you said is web-based.
Yeah.
So is it Zoom class?
No, it's
we are
record.
going
It's
to
asynchronous.
record it?
It's asynchronous recordings that have already been made.
Okay.
In 2016 would be the most recent ones, but this stuff doesn't change over that time scale. So the place you would access these is in Canvas, and so you really only need to use Canvas. Everything's served to you there. I mentioned before that under syllabus, not only are the course resources page where you can download the program, the syllabus, and the timetable are all there, but also you'll get reminded for your assignments to do here. But the individual lectures will be served to you. So tonight at midnight, you'll get an email. Make sure that Canvas is linked to your email so it gets delivered to your email box so you don't have to go looking on Canvas. And it will tell you what I would like you to do for this coming week. So it's in your own time frame, but on Tuesday, I'd like you to look at this video, and on Thursday, I'd like you to look at this video and use that to learn how to do the assignments, which will be due another week from then. So you can sit in your pajamas, eating a donut, as you wish, and do it, yeah, or do it in your office or whatever. So it's all served to you. So web-based isn't everyone's cup of tea. So if that doesn't appeal to you, then that's also a decision for you, right, as well. But that's the way that this is set up. So of course, I think in YouTube, you can only fast forward by 2 times. If you download them, if you have a downloader, you can go through them at 30 times. So an hour you can get through in 2 minutes. If you're very visually inclined and clever, or seen it before. So yeah, I don't know. I don't get a sense of. I think it's not daunting. Everything is explained. There's not there's not a huge number of things I can do in life, but I think I can explain this topic. I think across the board to anybody with any reasonable, not a strong math background, but a physically intuitive background. All the explanations aren't derivations of PDEs; they're physically based explanations, and so I hope that you enjoy it. It's been I think it's a good class, but then of course I would. Yep.
So you said COMSOL, it's like a free MATLAB software?
COMSOL is available, no. So MATLAB, I don't know if as a student you can get it for free. I think
Yeah,
you can.
you can.
So you can use MATLAB.
Oh, okay.
COMSOL, and it's also available on the clusters to access online. COMSOL and Abacus and ANSYS are big finite element programs which allow you to solve big finite element meshes and problems, and those are all available to you on the cluster, free through Penn State.
Okay, so the codes we saw, they have the same syntax as MATLAB?
That's not really the object of the class. The object of the class is to have you make the element subroutines so you understand something about well, you can solve it using MATLAB. Is that what you asked?
I'm just trying to confirm if it is.
You should use MATLAB to do these solutions, and in your presentations, the handed examples could be by MATLAB or by hand. The idea is you'll see when you start looking at these things, is I go maybe through, well, you see me go laboriously through this as it goes on behind me. is, and that's one of the few things where we have to use PDEs, but we don't use it. I'm not sure in this one whether we'll see it. Well, you see that exact problem that we're solving. I'm trying to explain exactly how it's done. This is the matrix equation that is part of the one we just solved using FreeMat, which is MATLAB. So this is the background to what you need to do. But if you want to get access to things like COMSOL and Abacus, you can. You just need to have your advisor ask for you to be given the count on the cluster, then you can access it. So if that's your ultimate goal in some of these things, that's perfectly viable. Okay. Yeah, that's good.
How do we submit our assignments when we are done?
You click the box online and you get 100% for that assignment. Unfortunately, if you don't click it, I guess there is not a no on there. So either you get no grade or 100%. Are you amazed by my trust? I'm not sure whether there's a spectrum, right? Trust or stupidity, I don't know which one. Trust, yeah. No, you guys can do it. If you want to do it, great. If you don't do it, that's not my problem. I think there's great things that you can learn from this, and that's the way that I'm pitching it. And so enjoy it. I think so. Yeah.
Yeah, about group presentations. Are
Yep.
they going to be in person? Or?
I don't know. It's left on there to, what are your thoughts? Do you want to do them? It's very easy. It's certainly easiest to do it and more convenient to be able to view them asynchronously and take a quiz. Or I guess the alternative would be to come into person. I guess in some of my classes we've done it both ways. The groups that want to do it in person, do it in person. And the rest of the class have to come along to participate. And the groups who want to do it online, do it online, and all the class do it online, because there is no in-person. So, what's people's thoughts? Or don't you want to say, or do you want to think about it? Are you interested in getting out of COVID and being with people? Or sitting in your basement and no? So, actually, what you might do is when you respond to perhaps I'll change it. I'll get you to respond to the topical areas, say online or in person. It won't be a perfect solution, but because it might not be unanimous. People want to do DM. Might be two want to do it one way and one the other way. So I guess maybe you take I don't have a preference one way or the other. As you see from the syllabus, maybe they're in the last three weeks of class, and we'd usually schedule them on a Tuesday, Thursday for some time that people can make, if there is such a time. I guess probably 5 o'clock on Tuesdays and Thursdays might work. You have a class that's done now. I know one other person has a class which is done at 4:30. Don't know if there are others who've missed this because of conflicts. Yeah, so I don't have a dog in the hunt on that one. I'm fine either way. So I'll change the request on Canvas to ask that. What else? So this screen recording, I will convert to MP4. I'll upload it on YouTube, and it will go perhaps on the course resources page. I don't think the other ones are for the previous years for the introductory one. Last year we were using Zoom, and so it didn't get done that way. But I'll do that. And so that's how the class works. So today is just the structure of how we do it. I don't expect you to understand necessarily anything about Hooke's law and Darcy's law and Fourier's law and Fick's law. You may already know that stuff, but you'll come across that in droves as you go through the class, I think. And I hope it's set up. It's a nice class. Deals with individually hydraulic, thermal and chemistry parts, and then mechanical, and then attempts to try and stitch them together in some logical ways, which again is quite straightforward, I think, quite logical way of doing things.